So there's yet another test for heteroskedasticity, which is called the White test for heteroskedasticity, named after the person who constructed the test. And this is similar in spirit to the Bruce-Pagan test or the BP test. But it also, so there are two versions. One is basically that this is going to include all of the explanatory variables that we had in the BP test, but it also includes other manipulations of those variables, like squares and interaction terms for all of the explanatory variables. Okay, so if you think about it, you can basically regress in that step with u square. When you're regressing u square on all the explanatory variables, you can have squared terms as well as interaction terms. And so you're basically going to look at the joint test that is reported once the joint F test that's reported in your output, okay, to see what are the inference that you can, what is the inference that you can draw for homoskedasticity. Now, the White test, both tests have pros and cons. So the White test has the advantage that it actually looks at departures from the null that could invalidate the usual OLS standard error. So maybe, if the functional form of the regression isn't specified correctly by excluding squared or interaction terms, the White test allows for that. But it has the disadvantage of using lots of degrees of freedom. As you can see, if you have a lot of squared terms and interaction terms, we can lose a lot of degrees of freedom very quickly relative to the original model. So a special case of the White test tries to correct for that. And the way that's done is basically regressing your U hat square, the squared errors or squared residuals on the predicted value of y and the predicted of y I square, right? So you're basically taking the fitted value in the regression and the square of the fitted values in the regression, okay? And in this way, we do not lose a lot of degrees of freedom because these are only two variables on the right-hand side. Okay, so that's the idea behind how you can test for heteroskedasticity. And of course, we're skipping the part on weighted least squares, but if you're interested, you can read more of that in the book. Basically, the idea is that if we, even if we do not correctly specify the form of heteroskedasticity, sometimes we can do better than OLS by using an incorrect variance function. Okay, and you can take a look at what weighted least squares has to offer.